All right, so for us to understand an atom model, we have to understand basically the general idea behind what an atom is. All right, so the first thing we want to talk about is an atom is what it is. It is the smallest piece something can be. 11. And still be it. Okay? Now that's my definition, just to make sure that we are, it's not a scientific definition, it's not a textbook definition. An atom is the smallest piece I can get something to be, but it still be it. By be it, I mean it still retains its properties. Properties is a word you're going to hear a lot throughout the semester, okay? Properties in science is a characteristic. It's a trait, all right? So it's something that is describing the material itself. So what I want to do is just give you a very quick example of what we would say an atom is. All right, so if we had a piece of gold, so let's just say we took a gold ring, all right, and then we ground it up into a powder, okay? So like we ground it up into like sugar. As a matter of fact, we could even say we ground it up into more fine sugar, like not the sugar that you put in your tea, but like the sugar that they have on those funnel cakes, all right, like that very powdery sugar, okay? If you took one of those little specks, that would still be probably 1,000 times bigger than an atom. All right, but if I ground up a gold ring into a fine powder, all right, what I mean by it still be it is that gold is a metal. So it's shiny, it's hard, and in the case of gold, it's got a yellowish color to it. So if I ground it up into a powder and it maintained its metallic quality, its shininess, its yellowish color, right, things like that, then it would still be an atom. Like it has to maintain its identity. All right. Once it loses the properties that make it its own identity, then it's no longer an atom anymore. Then it's going to be something smaller than an atom. Okay. But the smallest piece I can get something to be and still be it is what we call an atom. Now, atoms are made up of two parts, and those two parts are what we want to make sure we understand today, because it's those two parts that we're going to focus on in our atom models that we are drawing today. So, first of all, part one is the inner part, all right, also known as the center part of the atom. Okay, that was what Rutherford discovered when he was shooting the particles and they started deflecting in different areas. Okay, remember that was the experiment where I told you, like, if somebody was shooting a gun and threw a piece of paper, you would expect the bullet to go straight through the piece of paper. If it started deflecting, then you would get annoyed and then you would figure out what's causing it to deflect. Well, the inner or the center was that part. Rutherford's the one that discovered it. So what is that center called? The nucleus. Okay? So the nucleus is the inner part of the atom. All right? And the nucleus contains two things. It contains protons, which have a positive charge, and it contains neutrons. Neutrons which have no charge. Okay? That's what the nucleus contains. But most of the mass of an atom is based on the nucleus. Okay? Now, a couple of things that we need to know about here. We're going to throw you a couple of words. Okay? The first word that we're going to throw at you is the word atomic number. The atomic number is a number applied to an atom, all right? But that number is designated because it is based on the number of protons. All right? So an atomic number tells you something. Specifically, it tells you the number of protons. So, once you've written down that line right there, I want you to turn your attention to your periodic table. Okay? When you look at your periodic table, I want you to find the element carbon. Okay? Carbon is on the periodic table. It is kind of toward the center, but it's in the upper center area. All right? And so once you have found carbon, you will see a box. The box with carbon contains 4 sets of information. You've got the 6, you've got the C, you've got the word carbon, and you've got the 12.01. Okay? Of those 4 pieces of information, the 6 is the atomic number. Okay? So when you're looking at your periodic table, all right, the 6 is the atomic number. So that is the atomic number. That is the number that tells you how many protons the element has. All right? The important part about atomic number is the atomic number is used to ID atoms. Okay? That's what's used to identify atoms. If you look at your periodic table, your elements are arranged based on increasing atomic number. Because there'll be some, now you may look at the atomic mass, which is that decimal number that you see underneath the carbon word, 12.01, and you will notice that most elements, as you go to the right, tend to increase in the atomic mass as well. But there are a couple of spots where those mass numbers don't increase, they actually decrease. One of those examples you would say is found in elements number 27 and 28. If you look at elements number 27 and 28, cobalt and nickel, you notice that the atomic numbers increase from 27 to 28. But if you look at those mass numbers, which are below, those go from 58.93 to 58.69. That decreased. So that's why, again, when we identify elements, we're using the atomic number, all right? And the periodic table of elements is based on increasing atomic number. The atomic number is important, all right? Now, here's where you're going to have a hardship. This is where you're going to have some issues because there's another number we need to be familiar with. That number is called the mass number, all right? The mass number is a number designated by the number of protons and the number of neutrons combined. So the problem for you now is there are two words: atomic number, mass number. Both words have the word number in it. So that's not going to help you out. You can say, I remember it's that number word. Well, there's two of them now. Okay. Well, I'll remember that one because the atomic number is protons. Well, so is the mass number. Mass number's got protons too. So the only way for you to know these two is you got to remember what makes them different. And that is one contains neutrons in addition to the protons. The other one doesn't. So atomic number is number of protons only. The mass number is the number of protons and neutrons combined. Both of these things pertain to what we find in the nucleus, which is why the nucleus is going to be a very important part for what we look at when we're trying to identify atoms based on names and whatnot like that. So just kind of want to throw that out there, that they have the inner part. The atom is made up of two parts. The inner, called the nucleus, which contains your protons, which are positive, your neutrons, which are neutral. Neutrons have no charge. They're not negative. Okay? They have no charge. Your atomic number and your mass number are two words that we can get by looking at the contents that are inside the nucleus. The second part to the atom is the outer part. The outer part is what we call the electron cloud. Okay? The electron cloud, based on its name, is going to contain the electrons. The electrons have a negative charge. All right? The electrons have a negative charge. So now, something that I'm going to erase the top half because I need to keep going with number 2, but I'm going to go with the top. All right? But something that I need you to realize, there's a lot of information I would put underneath the electron cloud. Most of that information we already dealt with on Thursday last week when we talked about energy levels and orbitals. Okay? So let's review that real quick while we remember so that way we don't have to write it down again. There were how many different types of energy levels?
7.
Not 7. Okay? There were 4 different types. Okay? One type could hold how many?
2.
A second type could hold how many?
6.
Okay, don't worry, congratulations, you're both wrong. Okay, I'm talking energy levels, not orbitals. Energy levels is the big hallway. Orbitals are the rooms in the hallway. Okay, so again, there were, in other words, here's your confusion. There were 4 types of energy levels. There were also 4 types of orbitals. Okay, so let's get back to the energy levels. One of the types of, and here's the other confusion. There is a type of energy level that can hold 2 electrons. There is also a type of orbital that can hold 2 electrons. And then they have nothing else in common. All right? So therefore, the second type of energy level can hold how many? 8. Okay? The third type could hold how many? 18. And then the fourth type could hold how many? 32. Now, that's the hallways. The hallways contain rooms. The rooms are called the orbitals. The orbitals, there are 4 types. The S, which can hold how many? 2. The D, which can hold how many? 2. Say what? 10. I went out of order on purpose. Okay, just to see, are you just going through the motions, or are you paying attention to what you're actually saying? All right, the D orbital, which can hold 10. All right, and then the P orbital, which can hold how many? 6. And then the F orbital, which can hold how many? 14. 14. Okay, so those are the rooms within the hallway. All right, but the energy levels are the hallway. Who was the guy that established the fact that there were these hallways called energy levels? Bohr. Okay. All right. So now what I'm going to do is I'm going to erase this top part over here. So a lot of that stuff that we just went through verbally, I would normally write down in the electron cloud section, but we've already covered that, so I don't need to write it again. All right. But again, we're talking about electron cloud here. So what I want to make sure we do is I need you to understand this. There is a word that is a very important word. The very important word is called a valence electron. Okay, a valence electron. Now, first of all, based on its last name, I know it's an electron. But because I gave it a first name, that means I must distinguish that from another electron. Like, what makes a valence electron special compared to just an electron in general? All right, and the answer to that question is that valence electrons, those are the electrons in the outer ring. Ring is a energy level. All right. So number one, I know that these are the ones found on the outside. All right. But then now, if anybody else is inquisitive, then the next question they would ask is, well, why do we care about those that are on the outside? And the reason why we care about those on the outside is because these electrons determine an element's behavior and how it combines when forming compounds. All right, because at some point, you're going to have to, in test 4, we get into writing compounds. All right, and so sometimes you're going to have to know, if I take this element, who can this element combine with? Well, it depends on what kind of compound you're trying to form. Are you trying to form a molecule? Are you trying to form a salt? Or are you trying to form what? Well, again, based on the valence electrons, that's how you determine what you're trying to establish in the form of a compound. All right, so if you recall, there is a 10-step problem that we need to do by week 10. Okay, in stoichiometry, there is a 10-step problem. Well, today we're about to show you step 1 and step 2. Actually, they kind of go together. All right, which is this. If you cannot determine valence electrons for an element, then you cannot do step 1, which means step 2, 3, 4, 5, 6, 7, 8, 9, 10 will never happen. Okay, so the good news is you'll never have to worry about anything for the next 8 weeks because you couldn't do anything anyway. All right, because if you can't get valence electrons, step 1 is over. And so every step after that is not important. Okay, if you can't take a single step, then taking a bunch of steps is not really going to ever happen. So that's what we're looking at right there. Now, these words that we're talking about make more sense when we look at a model. And so that's what we need to do right now is we need to know how to draw a model. But there are a lot of things that you got to know. For example, how many electrons can one type of energy level hold? 2. What's going to another one be? 8. Thank you. All right. What can another one do? 18. Okay. And then you have one that can hold 32. All right. But now here's the issue. You don't have to memorize all that information, but you have to know where to get all that information. And that information is found on your periodic table. All right. So now what I'm going to do is I'm going to draw a model. And I don't want you to. I want you to watch me draw the model. Because then I'm going to show you how to draw the model. And I'm going to explain to you as you do it why everything in my model is exactly as it is. Okay? So take a look at carbon. All right, so find carbon. We already did. So if it takes you a long time the second time, then you really lost today. All right, so we got carbon on the periodic table, okay? The atomic number is 6, right? So we know carbon is the 6th element on the periodic table. So if I'm drawing the atom model for carbon, all right, the way I would do that is this. I'm just going to draw it. You don't draw it because right now we're going to draw it again. But this time I'm explaining it to you. Right now I'm not explaining anything to you. I'm just telling you this is how it is. All right? If it don't make sense, it ain't supposed to. Okay? So there is the atom model for carbon. All right? So you take a look at it, you know what I'm saying? Look at things and then just kind of say, all righty, I'm looking at it and I don't know what I'm looking. Whether you know what you're looking at or not is irrelevant. All right? If you can start to figure out what I'm doing, how I'm doing, great. That means you're thinking. All right? But that's what your atom model looks like. Okay? If it don't look like that, then you're wrong. Okay? Everything about that is put for a particular reason. Okay? Everything about our model is put there for a particular reason. Notice the dots in particularly. Okay? Notice the dots in particularly. So take a look at the dots, see where I got them put. All right? And then just kind of remember that. All right? So that way, because if you remember that, when I connect it in about 5 minutes, when I connect it, then it'll click a whole lot better and let you understand it a whole lot sooner. But if you're not paying attention where the dots are now, then when things get put together, you're still not going to just be like, oh, okay. And you're going to have to memorize everything. It's not going to gel, all right? But because I'm trying to tell you, right now, you can do this, and you don't have to memorize anything because everything's on your periodic table. But if you don't see how it connects, then you got to memorize everything. Like, for example, right now, you got to know one energy level can hold 2, one can hold 8, one can hold 18, one can hold 32. And that's fine because that's not that complicated to memorize. But there's a way that you don't have to memorize it at all, as long as you know how to look at it. All right? So, everybody got my model up here? Everybody see it? All right? If you were to have a question, think about what your question would be. If you don't have a question, then just don't ask me any questions later on in the semester either. All right? I mean, because if that's too much for you to think. Like, why did you fill in the blank? Like, if that's too much for you, then trust me, stoichiometry is going to kick your tail. All right? I would have said another word, but we're on video. So, all right? Are we good? I'm about to erase. All right.
What's that little dot right there?
Don't worry. I'm drawing it. I'm going to draw it again. I'm drawing it again. I know. I just want to know what your question was, JD.
Tell me what it is.
What was it again?
That little thing beside the N.
Beside the N?
Yeah.
I had an N up there? Oh, that little dot was my 0 for neutrons because they have 0 charge. You got what I'm saying? So, now I got you. Good question. Move that box. All right. So now, a couple of things here to realize. Easiest question for you. All right. What did I have in the middle?
Numbers.
Okay, great. Give me a number. 6. 6 what? 6p, right? Okay, so right now, okay, this should not be the hard question. So if you're like right now going, I don't know what he's talking about, that's not a good sign. Okay? So 6p, because I asked you what did I have in the middle, right? You said it's 6p.
Yeah.
What was that? Okay, how come I had that? How do you know? I mean, how did I know? Because of the atomic number. Okay, so again, here's what we're looking at right here, right? That's the atomic number. What did the atomic number stand for? Protons. That's why I had 6p plus in there, because I have 6 protons. How does he know? Because the atomic number is 6. It's not that complicated. Okay, so that's why. So again, I put a C. I put a C really just so that way you guys know I'm talking about carbon. All right, like in reality, it don't matter whether you write a C or not, because how do I know? How would I know what it is? I look at the proton number. When I look at the proton number, that's who I know it is. Okay, I don't have to write the word. I don't have to write the symbol. When I see 6 P's, 6 protons tells me it's an element that's number 6 on the periodic table. That's carbon. If I had 19 P's, then I know it's potassium. You see what I'm saying? Like if I had 5 P's, then I know it's boron. Okay, is that clicking? Like I don't have to write a symbol. Once I know how many protons it's got, I know who it is because all I got to do is go to the periodic table, find that atomic number, and know who it is then. All right. If I had 20 P's, I know it's calcium. So that's how it is. Okay. So I just want to say that's the connection there. So 6p plus. Why am I putting it at the center? Because what do we find at the center of an atom? The nucleus. What does the nucleus contain? Protons. That's why I put 6 protons. What else does it contain? Neutrons. All right. So now you ready? For right now, I put 6n0 because neutrons have no charge, right? Now, here's something you need to know because it's about to change in about 15 minutes or so. Okay? Right now, I'm going to assume that my neutron number and my proton number are the same. Okay? They always won't be the same. But right now, if I'm getting an element from here, I'm going to assume those numbers are the same. Okay? Because when those numbers are different, she's crazy. All right? And we call that an isotope. So right now, we're not worrying about isotopes because I haven't presented isotopes and I have not explained isotopes. So right now, for any model we draw, if I have not designated it as an isotope, then you can just say whatever the P number is, that's the N number. Because when they're different, she's crazy. Okay? Are we good right there so far?
Yeah.
That's my center because that's my nucleus. Because nucleus contains protons and neutrons, right? All right, after this, what did I do?
Circles.
Drew some circles. Great. How many circles did I draw?
2.
Okay. I drew 2. There's a reason I drew 2. Okay. It's real simple. Remember when we went over here the other day? Remember when I said row 1, row 2, row 3, row 5, row 6, row 7?
Yeah.
Okay. What row is carbon in?
2.
That's why I'm going to draw 2 rings. So ring number 1. Ring number 2. Why did I draw 2 rings? Because it's in row 2. What if I was drawing calcium? Okay, calcium is right here. How many rings would I draw? 4. What if I was drawing magnesium? Magnesium is right here. How many rings would I draw?
3.
So how do you know how many rings you need to draw? By the row that it's in. Carlos?
What if it's in the bottom?
If it's in the bottom down here?
Is
This bottom right here?
Yes.
Well, remember, I said the other day, these go right there.
Okay.
So therefore, this would be 6. This right here would go right here. These would be 7. So if I'm dealing with an element here, I'm drawing 7 rings. If I'm drawing with an element here, I'm drawing 6 rings. If you draw any more than 7 rings, you're about to be wrong. And you're about to do a whole lot of work to never, ever, ever be right. Okay? Because the most number of rings you can have is 7. Why? Because there are only 7 energy levels for the biggest atom that we got. Okay? Because as Carlos pointed out, he did you a favor. Them go right there. Them go right there. Okay? Are we good right now? Because I don't want to go fast and all of a sudden we still lost. Okay? So we're good where I got my 2 rings. Okay? Dontrell, we good? All right. My question now is this then. So now I got my 2 rings and you know how many rings to draw for any future element. The next question is this then. How many dots did I have laid out over there? 6. Okay, why 6?
Because there's 6.
Because I had 6 protons. Because remember now, every element should be neutral. Neutral meaning not have a positive charge, not have a negative charge, right? Well, if I got 6 positives inside, well then to be balanced, I had to have how many negatives outside? Okay, let's say that again. To be neutral, you cannot have a charge, right? Got to be equal. So if I got 6 positive things in the middle, then how many negative things do I have on the outside? 6, because 6 positives, 6 negatives are balanced, okay? So, now, here's the issue. The issue here is this, though. Most people would say, well, if I got 2 rings, draw 3 dots here, draw 3 dots here, nice and spaced, nice and even, and we're good. And you'd be wrong, because that's not the way the layout goes, okay? You cannot just say how many dots I have, how many rings I have, and then divide it up evenly between the 2, all right? Every ring can hold a certain amount. Every ring can hold a certain amount. Because remember, these rings, those are my energy levels. Those rings are my energy levels. Let me say it one more time. Those rings are my energy levels. So again, I have an energy level that can hold 2. I have an energy level that can hold 8. I have an energy level that can hold 18. I have an energy level that can hold 32. That ring right there, here's the question now, and here is the question. So those of you who have heavy eyelids, right? Again, don't have a problem with you drifting. Just don't bother me later. Okay? I mean, that's fair, right? I'm explaining it to you. You don't need to listen. You can't. If you need to stand, please go ahead and stand. Do what you got to do. Just don't bother me later. That ring right there is an energy level. The question you would ask is you would say, well, is that the one that can hold 2, 8, 18, or 32? Well, let me help you understand how to answer that question every single time. That's the first ring, right? So I'm going to go to the first row. That first row has hydrogen and helium. Okay? That first row has hydrogen and helium. So the first row has how many elements in it?
2.
So that's how many that one can hold. That one can hold 2. Mr. Sines, what if you got more than 2? Then you're going to put 2 of them there, and then you got to go somewhere else. Because that one's then full. Got it?
Yeah.
So, I've got 6 electrons, right? I'm going to put 1 right here and 1 right there. Mr. Sines, do I got to put 1 up and 1 down? Yes, because remember, what is the charge of that thing right there? Charge. Negative. What's the charge of that thing right there? Negative. Okay? Negative, negative. In nature, like kind do what? Repel. They're trying to get as far away from each other as possible. So that's why if one is up, the other one's down. Because that means they're repelling. They're not attracted to each other. They're trying to get away from each other. Go.
Can they just be opposite from each other, but not up and down, like left and right?
Yeah, I mean, they could be left and right, but ready? Any model you look at, it's going to be up and down. You know what I'm saying? Like any model you were to look at, it'd be up and down. So, but the whole issue here, though, is they have to be equally far away from each other. All right? So to answer your question, yes. Now let me add to that. Any diagram you're going to see, though, would always have 1 up and 1 down. So I just want you to get used to what you're going to see. All right. So I put 2 of my 6. How many left over? 4. Okay. So now, when I go over here, all right, I'm going to put 1 here, 1 here, 1 here, and 1 here. That way they're all equally far away from each other. You see what I'm saying? Because I got 4. They're trying to get as far away from each other as possible. So that way one's going to go north, one's going to go east, one's going to go west, one's going to go south. Once I put those 4, I'm done. I don't have any more, right? But here's my question. That second ring, because here's my, ready? Because somebody might be asking this question. Why'd you put 4 and you only put 2 in the first one? Can that one hold 2? Can that one hold more than 2?
Yes.
How many can it hold? 8. That one can hold 8. Somebody say, how do you know it can hold 8? Simple. Because I'm going to go to row 2. Ring 2, row 2. 1, 2, 3, 4, 5, 6, 7, 8. That's how many that ring can hold. It can hold 8, but you only put 4. I know. I mean, if the elevator says it can hold up to 5,000 pounds, right? Can it hold 1,000 pounds? Yes. Can it hold 8,000 pounds? No. It can hold less, just can't hold more. You follow what I'm saying there? All right? And therefore, there's my model. The way I drew it the first time, but now you explain it the way it's getting put together all the time. All right? So, and I'm going to add something now to you so that you understand what you're looking at. That first ring can hold 2, correct? Mm-hmm. That first ring can hold 2. Well, there's only 2 in that first ring. So how many orbitals would there be in there? 1 orbital? Which orbital? The S. And since it's in the first ring is the 1, and it's only got 2, so it's the S. So there's my 1S. Okay? Now, this one right here, right? It's got 4, correct? Mm-hmm. Well, it can hold 8. And I did this the other day. 2 for the S, 6 for the P. 2 plus 6 is what? 8. So therefore, this is the second ring. So this would be the 2S, right? And I have 2. And then I have 2P, and I have 2. All right? And so that's how I got, 2, 4, 6, which is my 6 electrons. So I'm just showing you how this is how this relates to what we did on Thursday. Okay? Question right now. Carlos, go ahead.
Well, it's not a question really, but
Go
I just
ahead.
figured out you can use the periodic table to see the 4 energy levels. They're not like in order, but like when you plug in the row that's not in, you can
Wait,
see
when did you leave my room?
Friday.
Oh, okay, never mind. Okay, go ahead.
But like the first row is 2, the third row is 8, and then the fifth row is 16, and the seventh row is 32. Wait,
Actually,
16 by 18. I think I just counted that right. I don't know.
I know. Say what you just said again.
So,
The first row is
2.
The second row is
Not this. Well, the third row because you skip a row. The third row is 8. The fifth row is 18, and the seventh row is 32. If you plug in the bottom one.
right. Okay. Well, listen. I can even make it easier. It's 2, 8, 8, 18, 18, 32, 32.
Yeah.
Right. Yep. Like you skipped a row. That's why I was getting
Yeah.
confused.
So you can see the 4 energy levels.
Yeah. Didn't I do that?
Yeah.
Okay, no. I'm just making sure. Okay.
If you plug in the bottom one.
I know. I could have sworn I did that on Thursday. Didn't I do that on Thursday? All right. Somebody am I doing? I thought everybody was here. Oh, gotcha. The magic man. Thank you very much, Mr. Mason.
Wait a minute.
So how you get the 2S?
How did I get the 2S? Because the 2 there is because it's in the second ring. All right? And the S, if you recall, all right, hold on. Gosh, this is where I suck. All right. This ends the first part of the video of drawing atom models. We still have isotopes to do.